Dear learner, welcome to this video lecture of Module 11 on semiconductor devices. This module will consist of 4 lectures, namely Semiconductor and Its Types, Semiconductor Diode, Transistor and Its Applications, and the last lecture will be on Integrated Circuit and its Applications. This is the first lecture of Module 11 under the online course on electricity and electrical wiring. In the previous module, that is on safety requirements, you have learned about the hazards and safety considerations of electricity and Indian electricity rules and regulations. In this lecture, we will discuss about the semiconductor materials, their properties, crystal structure, and various types of semiconductor material. By the end of this lecture, you will be able to explain semiconductor and distinguish between their different types. With these objectives, let us begin the today's lecture. Based on the electrical conductivity, all the materials in nature are classified as insulators, semiconductors, and conductors. An insulator is a material that offers a very low level conductivity when voltage is applied. For example, paper, mica, glass, quartz, etc. are the insulator materials. A conductor is a material which allows a flow of charge when voltage is applied across its terminals. That is, it has a very high conductivity. Some examples of conductors are copper, aluminum, silver, gold, etc. In Module 1, the conductor and insulators are already discussed broadly. So now let us start with the semiconductor. A semiconductor is a material that acts as a building block for many electronic components required for electrical wiring that control the flow of electricity by acting as a bridge between conductor and insulators. Semiconductor materials are usually used as active components within the circuit that can amplify, switch, or rectify electrical signals. A semiconductor material has the conductivity between the insulator and conductor. Two of the most commonly used semiconductor materials are silicon, which is symbolized as Si, and its atomic number is 14, and the other one is the germanium, which is symbolized as Ge, and its atomic number is 32. Both the atoms have 4 valence electrons. Some examples of compound semiconductors are cadmium sulfide, gallium arsenide, cadmium selenide, indium phosphide, indium antimonide, etc. They are used in many electrical devices such as sensors, inverters, power amplifiers, photoelectronic devices, etc. Compound semiconductors can make electrical devices smaller, faster, and more efficient. Now let us discuss the properties of semiconductor materials. The important properties exhibited by a semiconductor are: number 1, the resistivity of a semiconductor is less than an insulator but higher than a conductor. Property number 2 is that the semiconductors show a negative temperature coefficient of resistance. In other words, the resistance of the semiconductors decreases exponentially with an increase in temperature. Temperature coefficient of resistance is negative in case of semiconductor. The next property is that at 0 Kelvin temperature, semiconductor behaves as insulators. And as the temperature is increased, it works as a conductor. The next property of semiconductor is that the conductivity of the semiconductors increases when impurities are added. And this process of adding impurities to the semiconductor is called doping. The power losses are lower in semiconductor materials. And the current flow in the semiconductor is due to the electrons and holes. But in case of conductors, the current flow is due to electrons only. So next, let us move to the energy band diagram of semiconductor. So an energy band refers to the range of energy levels that electrons can have within a solid material. The energy band is classified as valence band, and the electrons in the outermost orbit are known as valence electrons. And these valence electrons contain a series of energy levels that form an energy band, and which is known as valence band. This band has the highest occupied energy. And the second band of energy band diagram is known as conduction band. The valence electrons are not tightly bound to the nucleus, due to which a few of these valence electrons leave the outermost orbit even at room temperature and become free electrons. The free electrons conduct current in conductors and are therefore known as conduction electrons. The range of energy formed by these conduction electrons is known as conduction band, and it has the lowest occupied energy levels. So next is the forbidden energy gap. The gap between the valence band and the conduction band is referred as the forbidden gap. The forbidden gap does not have any energy and no electrons stay in this band. If the forbidden energy gap is greater, then the valence band electrons are tightly bound to the nucleus. Some amount of external energy is required to that is equal to the forbidden gap energy. The figure shows the conduction band, valence band, and the forbidden energy gap of semiconductor material. The energy band diagram of semiconductors is shown where the conduction band is empty and the valence band is completely filled, but the forbidden gap between the two bands is very small, that is about 1 electron volt. For germanium, the forbidden gap is 0.72 eV, and for silicon it is 1.1 electron volt. Thus, semiconductor requires small conductivity. At 0 Kelvin temperature or at the low temperatures, the valence band electrons do not have sufficient energy to move from valence band to conduction band. Thus, semiconductors act as an insulators at 0 Kelvin. As the temperature increases, a large number of valence electrons acquire sufficient energy to leave the valence band and cross the forbidden band gap and reach the conduction band. In the conduction band, these electrons are free electrons and they can move freely under the influence of electric field. At room temperature, there are sufficient electrons in the conduction band, and hence the semiconductor is capable of conducting some current at room temperature. Inversely related to the conductivity of a material is its resistance to the flow of charge or current. Typical resistivity values of various materials are given in this table. An insulator has a very high resistivity ranging from 10 to the power 8 to 10 to the power 20 ohm meter. Resistivity of semiconductor ranging from 10 to the power minus 7 to 10 to the power 8 ohm meter. Resistivity of conductor is in the range of 10 to the power minus 8 to 10 to the power minus 6 ohm meter. Now similarly, the conductivity of these materials are shown in this table. In case of insulator, the conductivity is 10 to the power minus 10 to 10 to the power minus 6 per ohm per meter. In case of semiconductor, its value is 10 to the power minus 6 to 10 to the power 4 per ohm per meter. And in case of conductor, Conductivity is 10 to the power 4 to 10 to the power 7 per ohm per meter. So dear learners, after discussing the properties and energy band diagram of semiconductor material, let us now attempt some multiple choice questions to test our understanding. I hope you were able to answer these questions. Now let us move to the next topic, that is semiconductor types. Semiconductors are classified into intrinsic and extrinsic semiconductor. A pure form of semiconductor is called as intrinsic semiconductor. It is made up of only single type of element. Conduction in intrinsic semiconductor is either due to thermal excitation or crystal defects, that is the breaking of covalent bonds, which releases electrons that create an electric current. Silicon and germanium are the two examples of intrinsic semiconductors. Let us consider the structure of silicon. A silicon of atomic number 14, and it has 4 valence electrons, and these 4 electrons are shared by 4 neighboring atoms in the crystal structure by means of covalent bond. This figure shows the crystal structure of silicon at absolute zero temperature. The intrinsic semiconductor acts like a perfect insulator at absolute zero temperature due to the lack of free electrons. At the room temperature, some of the covalent bonds break up due to thermal energy as shown in this figure. The valence electrons that jump into conduction band are called as free electrons that are available for conduction. The absence of electrons in the covalent bond is represented by a small circle, usually referred to as hole. Thus, a hole is created when an electron in the valence band of semiconductor gains enough energy, that may be due to the heat, light, or an applied electric field. Then it can jump into the conduction band, leaving behind a vacancy or hole in the valence band, which is a positive charge. This hole acts as carrier of electricity in a manner similar to that of a free electron. The mechanism by which a hole contributes to conductivity is explained in the following. When a bond is incomplete so that a hole exists, it is relatively easy for a valence electron in the neighboring atom to leave its covalent bond to fill this hole. An electron moving from a bond to fill a hole moves in the direction opposite to that of electron. This hole in its new position may now be filled by an electron from another covalent bond, and the hole will correspondingly move one more step in the direction opposite to the motion of electron. Here we have a mechanism for conduction of electricity due to holes. Since an electron is a negatively charged and a hole is positively charged, When a potential difference is applied in an intrinsic semiconductor, electrons will move towards the positive terminal and the holes will flow towards the negative terminal of the battery. Therefore, the total current in intrinsic semiconductor is the sum of the current due to free electrons and holes. In this figure A shows a holes in 6th silicon atom or ion 6. Now you imagine that an electron from 5th neighboring silicon atom moves into the hole at 6th atom, resulting in the configuration shown in the figure B. When comparing figure A and B, it appears as when the hole has moved from ion 6 to ion 5th. Furthermore, when comparing figure B and C, the hole seems to move from ion 5 to ion 4. This discussion demonstrates that the motion of the hole occurs in the opposite direction of the electron's motion. Next, we will discuss the extrinsic semiconductor. The conductivity of intrinsic semiconductor can be increased by adding some suitable impurity atoms to the semiconductor material. When a small amount of impurity atom is added to this intrinsic semiconductor, it is called extrinsic or impurity semiconductor. And the process of adding impurities to the semiconductor is known as doping. The conductivity of semiconductor increases means either the number of free electrons or holes increases in the semiconductor crystal. When a trivalent impurity atom is added to the semiconductor, a large number of holes are produced in the semiconductor. On the other hand, addition of pentavalent impurity atoms creates a large number of electrons in the semiconductor crystal. Now, depending upon the type of impurity added, extrinsic semiconductor are classified into two types. They are P-type and N-type semiconductor. So first let us discuss the P-type semiconductor. When a trivalent impurity atom is added to intrinsic semiconductor, it is called P-type semiconductor. Trivalent atoms are those that have 3 valence electrons. Some typical examples of trivalent impurities are boron, aluminum, gallium, indium, etc. They are known as acceptor impurities because the holes created can accept electrons. Now let us consider that a boron impurity is added to pure silicon atom. Since the boron atom has 3 valence electrons, 3 covalent bonds will be formed with the 3 neighboring silicon atoms. The 4th covalent bond is incomplete as boron has no valence electron to share with silicon atom to form the covalent bond. This missing electron is called a hole. Therefore, for each boron atom added, one hole is created. To fill this vacancy, electrons from adjacent covalent bond can jump due to thermal energy by creating another hole in the adjacent bond. This hole is positively charged and the boron atom has a negative ion as it accepts the electrons. Thus, a P-type semiconductor has holes in majority and free electrons in minority, in addition with negative ions. So, dear learners, let us now discuss the N-type semiconductor. When a pentavalent impurity atom is added to an intrinsic semiconductor, it is called N-type semiconductor. Examples of pentavalent atoms are phosphorus, arsenic, bismuth, antimony, etc. They are called donor impurities because they donate one valence electron to the semiconductor crystal. We consider a phosphorus impurity atom is added to a silicon atom. The phosphorus atom has 5 valence electrons. 4 of these form covalent bonds with 4 neighboring silicon atoms. And the 5th electron is excessive and loosely bound to the nucleus. Hence, it is easily energized from the valence band to the conduction band by increase in the thermal energy. The energy required to detach the 5th electron from the impurity atom is very small, of the order 0.01 electron volt for germanium and 0.05 electron volt for silicon. Thus, at room temperature, its impurity atom donates 1 electron to the conduction band and achieved a positive ion. Due to the thermal energy, there will also some electron-hole pair generated because of the breaking of the covalent bonds. The number of free electrons generated by the pentavalent impurity is very large than the number of holes. Hence, an n-type semiconductor has electrons as majority carriers and holes as minority carriers, in addition, positive ions. Thus, current in n-type semiconductor is dominated by electrons, which are referred to as majority carriers. Holes are the minority carriers in n-type semiconductors. The conductivity of n-type semiconductor is greater than that of p-type semiconductor, as the mobility of electron is greater than that of holes. For the same level of doping in n-type semiconductor and p-type semiconductor, the conductivity of n-type semiconductor is around twice that of a p-type semiconductor. So dear learner, now we have come to the end of this video. So let us quickly move to the summary of this video lecture. So number 1 is all the materials are classified into 3 categories. They are conductor, insulator and semiconductor. Conductors have overlapping valence and conduction bands. Insulators have large forbidden gap. And the semiconductor materials have partially filled conduction and valence band and a narrow energy gap. Semiconductors are classified as intrinsic and extrinsic semiconductor, and extrinsic semiconductors are of 2 types. One is p-type and the other is n-type semiconductor. Trivalent atoms are added to obtain p-type semiconductor, and pentavalent atoms are added to get n-type semiconductor. Dear learner, let us now attempt some multiple choice questions to test our understanding of this last part of the lecture. So dear learner, this video lecture provides an overview of semiconductor materials. The session then covers the properties and energy band diagram of semiconductor, and by the end of the lecture, viewers will have a clear understanding of various types of semiconductor and the crystal structure of them. For further reading, you may refer to the following references. Thus, we come to the end of the video lecture. In the next lecture, we will discuss the semiconductor diode. See you with a new topic in the another video. Thank you.